Okay, so my clock says 3:03. So welcome everyone to the first installment in the year 2023 of the ATHENA X-ray Advances series. My name is Aurora Simionescu. In case you don't know, I will be your chair for this session today. And our speaker is Veronica Biffi. Veronica is a staff researcher at the Italian National Institute for Astrophysics at the Astronomical Observatory in Trieste. She's also an external associated member of the Computational Astrophysics Group of Munich University Observatory. So a lot of fun things in her life. Previous to that, she had postdoc positions in Garching, Madrid, Trieste, Boston, and Munich, so really all across the world. As you will see from her talk, her main scientific interests are cosmic structures and especially clusters of galaxies. And her talk will be about ATHENA's view of a galaxy cluster major merger. So Veronica, thank you very much for joining us, and the floor is all yours.
Thanks a lot, and thanks for the people who joined today. I don't need to introduce myself because Aurora already nicely did, and just let me say that the work I'm going to present has been done and published last year and was done in collaboration with John Zohon and the other people listed here on simulations of merging systems, merging galaxy clusters, and what we can see, what we can expect to see with ATHENA high-resolution spectrometer. So the ICM in clusters is a very interesting target for astrophysical studies and cosmological studies as well, because it traces the dark matter potential well of clusters, and it's very bright in the X-rays, so can be observed and can be used to reconstruct what we cannot see about galaxy clusters, like their intrinsic properties, total mass, or other dynamical structure of the potential well in which it resides. Also, it carries lots of interesting features and signatures of physical processes that go on within clusters, like accretion or infall of substructures and smaller systems, merging events, also with other massive clusters. And also, for instance, it has signature of energetic and chemical processes or feedback that take place in the gas, and also due to the interaction with member galaxies or clusters. Most of these signatures can be derived from X-ray observations. So looking at clusters in the X-ray band can give us a lot of different information about the gas itself and the cluster, the whole system in which the ICM resides. We know that from observations and from theory that this gas is not static, but there are lots of motions going on in the ICM, in the intra-cluster medium. These can be turbulent motions or bulk streaming motions due to several processes like AGN activity or accretion of structures and substructures, mergers with other systems, and for instance, the presence of shocks or sloshing cores in the center of clusters. They all basically produce large or velocities in general that have non-thermal origin. So they're not due just to the depth of the potential well and the equilibrium in the potential well, but can be different from that. And this contribution can be very important to take into account when you want to use clusters for mass constraints. So to weight galaxy clusters, for instance, for cosmological study, as we often hear. In these cases, it's important to quantify these motions and to quantify their contribution to the pressure support of the system. So from my perspective, if we use numerical simulations, then our life is a little bit easier than in the X-rays, because we can actually measure all these properties, especially the dynamical ones. And for instance, in the plot I showed here below the beautiful Perseus clusters, cluster, I selected this from a work we did in 2016, where we used indeed simulated clusters to reconstruct the level of hydrostatic equilibrium in the gas, so to quantify the level of motions there are that violate this assumption, which is at the base of mass estimates in the X-rays, for instance. And to relate this, and we could relate this to the mass bias that can be derived, that can be a consequence of this non-thermal contribution. And these are profiles of mass bias and violation of hydrostatic equilibrium, and we could relate the two quantities in terms of distance from the center in the simulated clusters. Why simulations? Simulations can be of several different natures. So we can have cosmological volumes simulated with dark matter and baryonic component. We can have zoom-in simulations of galaxy clusters, for instance, or we can have even idealized controlled simulations like those of merging systems that I'm using here. In all these different kinds of simulations, two of them are shown here in these images. We can have, for instance, not only the dark matter component, but also baryons inside. And we can use some models to describe the physics, the gravitational part of the dark matter, but also the hydrodynamics and the physics that drives the baryonic component, so gas and even stars, if we allow for star formation and cooling and star formation of the gas. The advantage of using simulations is that you can fully access the three-dimensional structure of your simulated system, so you can expect what is the intrinsic properties of the system. And also you can do this in different moments during the evolution of the systems or of the cosmological volume, so of the large-scale structure. So you can follow how the system evolves, and you can predict what is the origin of certain properties and what is the final configuration at the present time. Of course, this is useful from a purely theoretical point of view because you can validate your model assumptions, so you can assess whether the description of the physical processes you put inside the simulations is reasonable or not. You can make predictions for what to expect given your simulated system. And also you can basically compare with observational data set, which is the ultimate goal in the end. This will help you both to validate the models you put inside, but also to help what you can interpret from observational data, so what you can understand from what you observe in the real universe. And this last point is very crucial, but very delicate, because of course this can be done as long as the predictions from simulated systems are comparable to what you observe in the real universe. So there has to be an effort to translate the simulated results into what you would observe with a real instrument. Speaking about gas motions that I mentioned before, in simulations, as I said, you can directly measure or estimate these gas velocities because you have full access to the three-dimensional and intrinsic structure of the gas and the different components in the system, in the cluster. Observationally, this is much more challenging because in principle, you can use X-ray spectra and in particular the emission line coming from some heavy ions like iron to constrain the velocities of the gas, which produce a shift in the center of the line and a broadening, which is due to the peculiar velocity and which sets on top of the thermal broadening due to the potential well of the system. But in practice, you can do this only if the spectral resolution of the X-ray spectrum is high enough that you can really resolve the line and study its properties, so broadening and shift. And to do this in X-ray, in the X-ray band, you have to have instruments that allow you for very fine spectral resolution. This was shown with Hitomi on the core of the Perseus cluster, like in the, I put an image here of the beautiful spectrum they got in that case, and will be possible in the future with other calorimeters like the one on board GRISM or the XIFU on board ATHENA, and that's why I'm talking here. So with this few electron volts resolution, you can really study, again, this velocity feature on top of the emission lines, thinking about the iron line, for instance, around 6 kV. And from the simulation point of view, you can produce mock observations with mimicking the results that you can obtain with these instruments in order to predict what you can observe and to constrain whether what you derive from the spectra is comparable or not with what is inside the simulation, so with the true, let's say, intrinsic properties of the velocity field of the gas. And there have been works in the literature predicting this for, in particular for Itomi or Grissom and for ATHENA as well, other than the work that I'm presenting. In my case, the tool that I use to do these mock observations from the simulated clusters is called PHOX, and it's a code that I developed during my PhD, but there is a plethora of codes in the literature doing the same job. The main goal is to translate basically the hydro simulation output containing whatever system you like, clusters in particular for my interest, into something which is an ideal emission first, and then with a convolution with an instrument, a mock X-ray observation as similar as possible to what you would obtain from the real telescope. This code in particular takes care of really producing an ideal data set of photon emission in the X-ray band, assuming an emission model for the X-ray emitting sources in the simulation. So you generate a sort of ideal cube of photons associated one-to-one to the simulation output. And you can do this for the gas or for other emitting sources emitting in the X-rays, provided that you can assume a model to generate the emission. And we did this in the code also for AGN sources or for stellar emission from X-ray binaries with the work a student is doing at the USM in Munich. Second and third steps are to project the region, select a subregion of interest in your simulation if you want, or Doppler shift the energies of the photons due to some velocity along the line of sight once you choose the line of sight. And then final step is to convolve this ideal emission with the real characteristics of an instrument. And we did this for this work for ATHENA with 60, which is a dedicated software which takes into account lots of specifications of the instrument and provides you with a final event file from which you can extract images or spectra like the observed ones. So for the work I'm going to show some results of, we concentrated, as I mentioned, on mergers of galaxy clusters, because in that case, you expect to develop very significant motions, both bulk motions and turbulent macroscopic motions, due to the strong encounter of two systems. Especially if you look at a major merger, then you really expect to develop large velocities and even some complex velocity distribution along the line of sight that you can play with to test what you would observe in a mock spectrum. And the simulations we used were performed by John Zuhon at CFA, and they have been used in several works. And here we used one of them to do this ideal test. So we took a simulation of a major merger where you have two clusters with a mass ratio of 1:3, so really a major one. And we used a very ideal extreme case in which the impact parameter between the two clusters is 0. So you have a head-on collision between the two cores, which are very massive, very hot, as you see from the parameters I copied over. And in the gallery below, you see the evolution of the temperature map from the first moment till 10 gigayear after the beginning of the simulation. This is, let me say it again, a controlled ideal simulation. So it's a study case. There is no cosmological evolution inside, and there is no model for star formation. So it's only dark matter and gas. And we really want to see in this very ideal setup what we can measure from a mock spectrum, which is obtainable for GRISM and ATHENA. We did both cases. In particular, we concentrate on a snapshot in time, which is this one after 1.6 gigayear from the beginning of the simulation, which corresponds to the moments soon after the first core passage. So we want to study basically the ICM velocity structure in this configuration, and we did it for 2 line of sight. Again, extreme cases to constrain the range of possibilities, let's say. And I'm going to show results for this configuration here, which is with the line of sight aligned perpendicularly to the merger plane. So this is zooming into the maps of the ideal surface, X-ray surface brightness obtained from the simulation. So no instrument inside, it's only the emitted emission in the X-rays. And on the right, you have the map of the line of sight velocity dispersion of the same system in the same configuration. On top of it, I placed several pointings, which have a field of view of roughly the same size of GRISM, with which we started our tests. And we placed them in several different locations across the system, characterized by different properties in terms of brightness and in terms of velocity. And I will, so we did our exercise with GRISM on the very bright pointings here in the center, which have different velocities. But ATHENA will be, has demonstrated to be a major advantage to look at the faint ones. So like this one and these 3 here, which are fainter, but have very interesting velocity properties. So let me first give a few details about the simulated structure, so the intrinsic properties of the velocity field. And let me, as I said, concentrate on the pointings we used for ATHENA, so the faint ones, these 4, 1, 2, 3, and 5 pointings. Here I show the histograms of the velocity of the gas along the line of sight, so velocity on the x-axis, and the distribution basically of the velocity along the line of sight in each pointing. And the different curves refer to the mass-weighted distribution, which is in black, or the emission-weighted one with different weights, but all related to the X-ray emission of the gas. And you see that the complexity already pops up, the complexity of the velocity field along the line of sight. In particular, given the geometry of this merger, here we are in particular around the shock, which develops, and the envelope of the shocks, which develops after the core passage. And you see that, in fact, all pointings are characterized by a double peak in the velocity field, which corresponds to the 2 symmetrical sides of the shock that expands. Only in the offset pointing here on top, you see that when you look at the velocity field weighted by some X-ray emission, you lose the information of the double peak and you have just a broadened distribution. So we try to to generate mock observations to fit the iron lines or the whole spectra and constraining with the iron line to get a center shift and a broadening of the line, which would correspond to the broadening or to the width, if you want, of this distribution. And of course, you already see that the ones below are quite complicated. So we see what we can expect if we fit with a single velocity component. These are interesting not only because they're faint, but because they are characterized by several different velocity levels. And for instance, the Z5 pointing here is characterized by several hundreds of kilometers per second velocity dispersion, even though it's a very faint one. So we can already expect it will be a challenging measurement. So from the simulation, we can derive the expected velocity shift and velocity broadening, and we can compare with what we find from the spectra. This is what I was mentioning before. From the simulation, we can derive the estimates directly by fitting this distribution or by computing really by hand, let's say, the shift, the average velocity, so the shift of the line and the broadening of the line. If we assume a toy model for the iron line, you see that these distributions become like in the plot I show on the right. So they lose again the double peak in the case of iron emissivity weight in the first pointing, but in the other ones, you do preserve this very symmetrical double peaked shape of the line. And this is what we want to fit in the spectra as well. The phase diagrams in the middle are just here to provide an idea of how complex this situation can be, even in a very ideal geometrical case like the one I'm showing. Because, of course, it's not only a matter of velocity, but also different thermal phases of the gas along the line of sight are coexistent, and they have maybe different velocities. So this will be a complication in the spectra as well. When we did our test with GRISM, we could have very nice results for the brightest pointings that were placed more or less in this region in the system. But to get reliable constraints on the velocity from the iron line in these 4 faint regions, we had to increase the exposure to at least 1 megasecond. So not even 500 kilosecond exposure with GRISM could provide us with reliable constraints in these very faint areas of the system. And that's why we wanted to test the same exercise with XIFU of ATHENA because of its very large effective area, which would provide us with much larger photon counts. And indeed, with 100 kilosecond exposure, we could obtain observations and spectra from them, which were possible to be analyzed, even though we had to take into account some background component to be more realistic, let's say, because they're faint and we expect background to be important in those regions because of this. So we computed from the simulation the expected values, accounting for pointings which are a little bit different in size and shape to account for the different shape of the XIFU detector, let's say, field of view, sorry. And we derived iron emissivity weighted estimates from the simulation, which are center shift and broadening in these 2 columns of the table. And we compared those directly with what we could fit, assuming some velocity broadened model for the spectrum. So this is an example of one of the pointings with XIFU ATHENA for the 100 kilosecond mock observation. And on the right, we have a full spectrum in the 0.210 keV band with all the different components, background included. And in this pointing here, which is offset with respect to the merger axis and a little bit brighter, you see that the iron line is more or less visible on top of the background. And so this is the case that indeed we could fit better the spectrum. In all the other cases, we did the fit over the whole band because taking only the iron line was not enough to constrain the velocity. So in general, what we could see is that there was a major improvement with respect to the GRISM case, because here we could indeed find best fit results consistent within 1 sigma or at most 2 sigma with what we expect from the simulation. And we have to keep in mind that in almost all cases except this first one, the distribution of the velocity is very complex, as I showed before, because it has 2 symmetrical components, which is very difficult to fit. What we did is a very basic fit with 1 single velocity component, which should capture a whole average broadening of the line. It's not a perfect fit because you should in principle model the real distribution with by hand, let's say, function. So even in this very approximated case, we could find something very similar to what we find in the simulation directly. For another pointing among those, which is the one placed on top of the shock, we did a different exercise. We produced a 1 megasecond exposure mock observation with XIFU ATHENA to see whether it was possible to reconstruct the gradient that you expect across the shock in temperature and velocity. And to do this, we considered different annuli. We placed on top of this pointing 5 annuli of 20 arc-second each. As you can see in these 3 images, the one on the right is the mock XIFU pointing with the annuli on top. And on the left-hand side, you see temperature and velocity dispersion maps directly from the simulation, so ideal ones. Where I reconstructed the XIFU pointing and the annuli to get the same regions to have the predictions of the expected values from the simulations. Even in these cases, you have complex velocity distributions along the line of sight. And so fitting one spectrum per annulus, you can again try and get a best fit temperature and velocity dispersion in particular. But what you end up with is this kind of comparison. So in terms of temperature, you do see the gradient that you expect from the simulation. And you see that you have different results depending on the region of the spectrum you consider for the fit, but also the way you estimate the theoretical value from the simulation, which can impact also the comparison, because in simulations, you have the velocities, you have the temperature information, but you can get an average value, a different average value depending on how you compute it, how you estimate it. So again, thinking about a mass-weighted average or an emission-weighted average with different kind of emissivity, either from the map or directly from the simulation. And you see that in general, for the temperature doesn't change too much, and the gradient is more or less reconstructed with the best fit results from the spectrum within the uncertainties. So if you consider the emission-weighted values from this map and you compare with the blue data points from the best fit of the spectra, you do see that the gradient is more or less reconstructed. For what concerns the velocity broadening, the value themselves are consistent with what you expect from the simulations, but the uncertainties from the spectra are quite large. And also you have difficulties in reconstructing the velocity because, again, you have a very complex double peak distribution along the line of sight due to this symmetrical expanding envelope of the shock after the core passage, which is difficult to be captured in modeling the line from the spectra. So there are all these complexities adding on top of the photon counts, which are not that many, not even for 1 megasecond in the fainter annuli on top of the shock, which basically interplay and gives you this quite uncertain reconstruction. So in principle, if you have no guidelines given by the theoretical values, I would say you couldn't place too stringent constraints on the velocities from the spectra only. So this is an interesting exercise because it tells you basically that even in a very ideal case, in a very major merger where you have large velocities to be measured, it's difficult to reconstruct them with mock observations. So in the real case, it will be probably even more difficult because you don't even know exactly the three-dimensional geometry or the line of sight structure of the velocity field. Yet you can have nice global measurements with ATHENA, which were not possible before and which will probably be very difficult and challenging with other instruments like GRISM in faint regions in clusters. And this is the case for major measures, but you could have also similar interesting velocity regions in, for instance, the outskirts of, or at least intermediate regions of clusters where you have fainter emission, but you would expect probably interesting properties in terms of velocities. And just to summarize, what I've been showing so far is a theoretical study, still an ideal one based on numerical simulations, which, however, is useful to test what you can expect with this kind of high-resolution spectrometers that were mostly not available so far, except for Hitomi, with which you would like to measure directly velocity properties of the gas, for instance, in clusters from X-ray spectra. And we did these exercises in the simulation community several times, also in the past, also with predictions of precursors of ATHENA or for GRISM, not only in this work, but also in other works. And I would say there has been a lot of effort in the community, in the theoretical community, to try and test how well we can provide results that can be used or can be interpreted by observers, because they are a little bit more realistic, a little bit more similar to what you would observe, always with the caveats of doing this as a theoretical exercise, but with all the best effort. And I think I can conclude here if there is a question or more.
Okay, thank you so much, Veronica. We have lots of time for comments and questions, and thanks for the very nice talk. I'm going to take chair prerogative to start with my general feeling based on what you've said. I feel like there's a big hype in general about big data recently. And everybody's sort of excited about this machine learning prospects and all sorts of complicated algorithms that deal with big data, big volumes of data, lots and lots of measurements. And I think what we're heading towards with ATHENA, and based on what you're describing, is actually something similar, but in a different vein, is complex data. So we're not going to be having terabytes upon terabytes upon terabytes of observations that we have to deal with, and millions and trillions of parameters or things that we have to understand necessarily. But it is a complex data set, and what you are doing, your work and what you've discussed, it really reveals a whole new challenge in trying to understand, trying to make sense of that data. So I guess my first question to you would be, do you have, as an observer myself, do you have any advice for us? Imagine yourself that finally we are at the moment where we're receiving ATHENA data and we're all very excited and we want to publish papers. What would be your advice to someone like me who wants to understand those photons, not having access to the 3D information and to the multi-velocity structure that you've been describing? How should we go about that?
Yeah, I think, so one message I wanted to give is that we actually wanted, even from this theoretical exercise, the first idea was to explore different configurations, different line of sight, different moment in time, and then we stuck on this only snapshot in time and only case, because it was so interesting to try and understand what we got from the spectrum and what and how it was different with respect to what we expected in the simulation because of this complexity. But the message I want to give is that despite this, when you have like a global measurement in a region where you, as I said, you just fit for a velocity broadening and a velocity shift in a whole region, in a whole pointing or region in a map. So with a simplified model, because you do not know the complexity along the line of sight, and you wouldn't try with the photon statistic to do multi-components. It's difficult. Even here, even in the 1 megasecond case, it was impossible to use, not impossible, it was very difficult to use a multi-component fit. Even in that case, you can get reasonable measurements that provide you with a quite accurate description of the global amount of motions in the ICM. And of course, this is a very specific ideal case where you have these two components because of the symmetric expanding envelope. But in the real case, it is more likely that you have a complex broadened shape of the line. Maybe it's not Gaussian, so you will not have a perfect description with a simple model, but still you can get, you can really expect to get a measurement of the velocity. And that is already a huge step further in the analysis that we've been doing so far, I think, that you've been doing so far, providing us whether we do model correctly or not.
Well, I suspect we'll come knocking on the simulator's doors a lot more often than we have been up until now, at least.
Yeah, no, but I would go for, again, for velocity maps as much as possible, because this is really something interesting and we've seen really little of it because of practical difficulties.
So let's open the floor to other people. I see. So let me just say, first of all, if you have a question, if you haven't seen it yet, there's a Q&A icon in the taskbar at the bottom. So please type your question if you have one, or you can raise your hand. So I can know to give you the floor, and in order in which I have seen things, and I apologize if I've misseen things in order. I saw Matteo's hand up first, and Matteo, I think you can unmute and tell us your question.
Yeah, if you can hear me, I can ask. Thank you, Veronica. Very, very interesting talk, very exciting potential results. I have a very earthly and low-level question. Looking, for instance, at the spectrum you show in this slide, the XIFU spectrum, you seem to be dominated above 2 kV by a flat line, which I guess is the instrumental background and not X-ray background. So my question is, do you have an estimate of how much your results depend on our knowledge of the instrumental background? Because this is a critical parameter that we are assessing in the reformulation of ATHENA.
Yes, so we did here, I was maybe too quick before. So what we did was to try and reconstruct the values with and without the background. With the background, we had to assume it and put it on top of our data, of course. So in this case, I'm always a bit skeptical about studies on the background because we put it in and then we fit it in the final spectrum. So it certainly has an effect because the model in the end, because of photon statistics, is affected by your by fitting for the background as well. But in this case, we basically fixed the we fitted for the normalizations and we tried fixing them, but it didn't change too much essentially. So I think this exercise was not super useful to place constraint on that. And this line, yes, is the instrumental background that we took, like the requirement for ATHENA at the time we did it.
Thank you, Veronica.
And yes, especially at high energies, here was really dominating the results, but still we could provide some consistent estimate of the velocity by using the full range of the spectrum. So not the iron line, but the full 0.2 10 kV band. And in the table I was showing before, we had different values when also the background is included, which is these two columns here. And as you can see, it's not that much worse, let's say. But again, we know the background here because it's a model we put inside. So it's not something given by the universe.
Okay, perfect. Thank you, Veronica.
Okay, then the next thing I saw was in the Q&A, a written question by Earnest Mayunder, who I happen to know is one of our Estron PhD students. It might be a question for me more than for you, but I'm going to read it out anyway. How many counts do you need to resolve the same line shifts and width with CRISM? Based on this, how far can you look with CRISM for such a merging system? I think the heart of the question is, what areas will XIFU open to us that are not accessible with the CRISM capabilities? And I think you've already said that, but maybe you can give us a sense of, where does it become feasible to use CRISM for this science?
Yes, I mean, we did use CRISM in this paper, and we used it for the bright pointings in the center. For these faint regions, basically with ATHENA, we had 5 times larger number of counts with lower exposure, essentially. So we did try with CRISM, but it was not possible to put constraints on the velocity in these super faint regions. For instance, in the case I'm showing in this slide, so the same system, but looking at it along the merger axis, we did use GRISM and successfully, and we could even, this is a GRISM-like spectrum that we did in this paper, and this is the distribution of the velocity of the 2 cores, basically, which is not symmetric because they are different in this central pointing here. And we did find very nicely the 2 separate components in GRISM spectra. So it's not, I mean, again, this is a very bright pointing, similar to the core of Perseus where it was used in Itomi. I think ATHENA will be a major difference in the fainter regions. But I'm not an observer, so this is what I saw.
Can you give us a sense of the physical scale? I think we're talking about the region you're mentioning with CRISM was maybe a few hundred kiloparsecs.
Yes, yes.
Yes. So anything more than a few hundred kiloparsec is ATHENA territory.
Yes, it depends also on the redshift where the system is, I guess. But then, of course, with a farther system, you have a larger region accessible with GRISM, but then it's fainter. So again, yeah.
Then I hope, Earnest, that we have answered your question and I didn't misinterpret it. If I did, just please follow up in the chat. And then after that, I think in order of seeing things, I saw Didier's hand up first. So I think maybe Didier, you can unmute and say your question.
Okay, thank you for the talk. It's a very nice talk. As you probably know, we are reformulating the mission. We are reformulating the instrument. Some performance parameters will be hit by this reformulation. A similar question to Matteo, but on a larger range of parameters. So what is at stake today, I think it is in the reformulation, is the XIFU field of view, the XIFU spectral resolution, the 1 keV effective area, the 7 keV effective area, which is not, I mean, it's connected not only to the instrument itself, but also to the mirror, to the later two, and the background reproducibility or background knowledge. So if you were to rank those performance parameters for this particular science, what would be your ranking? I would probably consider only 3 performance parameters: the field of view, the spectral resolution, and the 7 keV area. What would that be your rank? What would your ranking be for this?
You mean for this exercise in particular, or?
Yeah, I mean, yeah. If you were to ask me which parameter I should degrade the least, what would this be?
Well, I mean, for these studies here, probably the spectral resolution would be my favorite still. Field of view, not necessarily, because, I mean, it depends, of course, on how much is reduced. But here it was, I think the main difference in this very faint region was done by the effective area and mainly the effective area with respect to Grissom. So yeah, I think spectral resolution and effective area would be my favorites.
But because of the line, the different mechanism entering in the line broadening, you do not, I mean, you have lines which are broader, significantly broader than the intrinsic spectral resolution. So for you, would that make a difference for you to go from, say, 2.5 eV to 4 eV? How much would you read? I mean, it's tough. It's a tough question. I understand.
Yeah, it's tough to say. Tough to say. I mean, we did some tests with few EVs, theoretical ones, so without using 60 or the specifics of ATHENA. Also in the past, up to 3, 4, 5 EVs, and as long as you have enough photons, you still can get nice constraints on the thinking about the iron line, because there basically the broadening you have is almost entirely due to non-thermal motions. So there it's anyway fine. Maybe I didn't try myself, but I expect in those cases it's more difficult to do the exact line shape study like they did, for instance, with Itomi. In some cases it can be more difficult, but again, for getting a sense of the level of motions you have, you would first try, I guess, with a single component, a single broadening, let's say. So in that case, probably it wouldn't make a lot of difference, but I wouldn't bet. I didn't try specifically.
Oh, thank you. I think I agree with you that counts is what counts at the end, and effective area, I think, for this particular science is really what we should push for. And this is a message to Matteo to keep pushing on ESA to make a better mirror in terms of effective area.
Also to be maybe complementary with other instruments, like not even better or worse, but to give a piece of information more, right?
Thank you very much.
You're welcome.
Okay, then the next thing I've seen on the Q&A is a question from Ian Ling Chen. Actually, good representation from the Astro students today. Shameless self-promotion by me. So Ian Ling is asking, thank you for a great talk. I wonder, will it help if we make narrow band images, which can alleviate contamination from other redshifts and probe velocities in the ICM, or is it better to just fit the spectrum? So yes, the question is between looking at narrow band images and directly fitting the spectrum. Is it worth to do both, or would you stick to the spectral fitting?
I didn't try the other way, actually. I've always worked with the spectral information. Yeah, I actually wouldn't know. That's interesting. Maybe we should try. We do something similar when we weight the maps, for instance, the velocity dispersion map by a certain emissivity in a band, probably. But yeah.
Yeah, there are some nice, I think, Muse visualizations based on Muse data cubes that I've seen on the ESO website, and Alma is doing similar things where you can kind of make a movie as you move through various slices in energy. So it's maybe worth thinking of different visualizations that we could look at with ATHENA as well based on this.
So, but for the redshifts, I think there is no issue there, right? Because, I mean, you have the shift of the line given by the bulk velocity of the gas, whatever the reason is, but I don't think you have contamination by other redshifts. I mean, the emission from other redshift sources will go into the background, I guess.
For massive clusters, you're probably correct. If you are looking at much smaller systems like circumgalactic medium halos, for example, where you have many more of them potentially along the line of sight, then you run into this problem.
But
for clusters, indeed.
But in those cases, you have other issues in the first place because you're not talking about the iron line anymore if they are too low temperature. So yes, the lines at the lower temperature, then it's more complicated. It's a different story because there you have the thermal broadening plus other contribution. The lines are crowded. It's different. Yeah.
Then next among the things I've seen is a question in the Q&A from Floren Castellani, asking which configuration have you chosen for XIFU simulation, number of pixels, angular resolution?
I should check now. I don't remember anymore, honestly, by heart. I should check. I'm sorry. Probably in the paper is written.
If I can answer this question, I believe you use the official release of 60, which I think has the previous configuration of XIFU with 3,000 pixels or something, 96 channels. I mean the
4,096.
Because we have not released anything to the community, anything else to the community. So you must be using what we call the IPRR baseline configuration of XIFU.
This is the one. The one I think from 2019.
Yeah. That's the one. Yeah, that's the one we described in the 2018 SPI.
There were other works based on MOC from simulations on clusters by Cucchetti and other people, and it was basically the same configuration. Yes.
There will be for everyone attending this telecom. There will be soon a new release of 60 for the SRDT to run some simulations. We are working on this.
Okay, we are coming slowly close to the end of the hour, so I want to give the last chance for a question to one of our participants who has their hand raised. I've asked if we can unmute you, Kazu Nakazawa. I think you might be able to actually say your question out loud. Hi.
Thank you very much. Can you hear me?
Yeah, thanks for joining us from Japan. It must be
quite it's nearly midnight. A very nice talk, and it stimulated me very much about the future about this study. And because your study is so clean and bright, I had an imagination that when you simulate the shock front, then you'll see the ionization temperature, kinetic temperature, and the turbulence changing below the shock wave. And it will be give us a very new idea about the post-shock contribution. For example, electron temperature may be rising rapidly, or the kinetic temperature of the ion may be rising rapidly. But the ionization needs, collision. So the electromagnetic blah cannot do the ionization, and that will tell us about the turbulence or the status of the shock front. Are there any plan to implement that kind of a, physics in your simulation so that we can understand what's going on in the shock front of the clusters?
So this would be actually, this is very interesting indeed, and it's not the first time comes into place, let's say, but this would be a question for John, who performed the simulations, and these ones are very ideal ones. As I said, there is only the basic hydrodynamics. There is not even the complexity of the other physics, like again, star formation and all these processes that would complicate even further already this nice picture. And certainly there is not yet what you mentioned.
Because angular resolution is a very strong point of the ATHENA. And that will be a very, no one can access with QUISM kind of new science there. Yeah. So I wanna, very interested to see that kind of a result in maybe near future.
Yeah, that would be certainly something interesting. Yes.
Yeah. Thanks a lot.
So with that, thank you very much, Veronica, for this talk.
you.
I think we had a lot of discussion at the end, so it was very nice to see a lot of people participating, also asking questions. I mentioned at the beginning that this was the first seminar in this ATHENA X-ray Advances series of this year. Of course, we had many installments of this last year, and we will continue to do this about once a month from this year from now on. So if you enjoyed this, then please tell everyone to join the next version of it, and please join it yourself. So our next ACO Science webinar is going to take place on the 28th of March, and the title will be Athena's Cosmic Hunt to Discover the Riches of Neutron Star Interiors. So that sounds like a very exciting topic, and our speaker is going to be Sébastien Guillot from IRAP and Université Paul Sabatier. So we hope to see you next month, and with that, thank you very much for joining again.
Thanks. Thank you.